Is something kicking off? Oh. All right. So the first part of this session is going to be more theoretical rather than actually going to be more about the practice. I'm talking more about the practice later today. So this session is going to be more theoretical in nature. So I'd rather take questions at the end if that's okay. So I'm trying to sort my notes. I'm not good first thing in the morning. All right, so what I want to talk about is data culture, more about the network and the data and the theory behind why data is so important. I want to talk a little bit about why we are where we are in the world of data at the moment. All right, so I should introduce myself. My name is Jen Stirrup. Someone who's been in the data visualization space for a long time. And I've written a few books on Tableau, believe it or not. I also work with lots of other technologies, including Microsoft Azure. And we're here today to talk Power BI. Okay, so the thing is that we are designed as humans to look for patterns. So we tend to look at data to try and find patterns in it. There's a whole process in the way that we react to data. So when we look at some of the COVID data, what we do see is people's reactions to data coming out. They sometimes ask questions of it. Unfortunately, we have seen some examples where the interpretation of the data is coloured by people's preconceptions about other countries. So we see that as well. So when we look at data, we are not always simply just looking at the data itself, we bring ourselves to it too. So this is one of my favourite quotes by Terry Pratchett. I'd be more enthusiastic about encouraging thinking outside the box when there's any evidence of thinking going on inside it. And that's very true. We need our house in order when we start to think about data. So what types of analysis do we actually do? Some of you may recognise the Gartner deck for that. Gartner talk about descriptive, diagnostic, predictive and prescriptive analytics. So I've tried to translate that to the actual business question that people are asking. So Power BI is very good for answering why types of questions. It allows people, as we know, to click and tick and get the answers to the data that they need. And it's very good for that. But I still maintain there's also a place for reporting services as well. The world will always need structures, canned, financial and fairly boring reports. But we're very lucky that Power BI lets us do both. All right.
Jen, to interrupt,
yes.
You need to share your screen, please.
Just what? Sorry?
You need to share your screen.
All right. I had real problems getting into Teams this morning. All right, sorry about that. I just had so many problems getting into Teams this morning that it just threw me a little bit. Okay. All right, so here, just to step back a little bit, as we start to think about the types of analysis that people are looking for. So when we build our Power BI dashboards, we need to try and understand the business question and what people are actually doing and what they're asking us for. Often you can hear customers saying things like, I want a CSV file or I want a dump of the data. What that usually tells me is they don't always know what they're looking for, but they don't want to miss anything. So what we're trying to do is give them a good structure where they can click and tick and get the data that they need and get the answers to what they're looking for, but without necessarily having to go in and play around with the data themselves. So when people are wondering what the business question is, what I try and work out is it a business puzzle or a business mystery? So with a business puzzle, we have a very well-defined question and a very well-defined answer. Something like, tell me the sales for a particular product for the last year, for example. So that's a puzzle, which is a very specific question and a very specific answer. And that answer will be correct anytime that whatever technology you throw it at. The other item that they might be looking for is a business mystery, where they can't really understand the question and they don't really know what they want, and they won't know the answer definitely every time they ask the same question. So I worked with a mobile phone giant a few years ago. They were trying to understand why people left their mobile phone firm. Why did they choose another vendor? And the business question was really, why do people leave us and where do they go next? So the interesting thing there was really about the first question was well defined, but we couldn't ask any other questions until we got the answer to a simple breakdown of where people went. And then that engendered lots more questions after that. So that kind of thing is usually a business mystery. So Power BI is very good at business mysteries where people don't really know the question and they don't really know what answer they're looking for. These are the sort of engine that run business questions. Okay. So what we have here is chaos applied to data. So when we look at chaos theory, systems look quite disordered, or they can do, and it's about finding underlying order in apparently very random data. But chaos is not disorder, it's a transition between order and disorder. So we have something called the butterfly effect. And what that really means is that the flapping of a single butterfly's wing today produces a tiny change in the atmosphere. But over a period of time, what the atmosphere does actually diverges from what it would have done. So in a month's time, for example, the scenario is a tornado that would have devastated the Indonesian coast doesn't happen. And maybe one that wasn't going to happen actually does. So we get that from Ian Stewart's book, Does God Play Dice? The Mathematics of Chaos. And what we're trying to say is that data can be very sensitive to initial dependence on initial conditions. So a tiny state in an atmosphere can actually produce a great result. So when we look at data, it's good to try and work back to understand where did that come from. So it can be good to understand the source systems as well. So it's something to think about. So how can we control this chaos in the environment, which is the line between order and disorder? Well, chaos theory itself can help us to understand the variables that affect a system, thereby helping us to reveal the underlying patterns. So it'll be easier to predict outcomes when that happens. We've also got quantum chaos as well. We talk a lot about everything's quantum at the moment. Quantum mechanics would predict that a given system is the sum of its parts and should behave as an output X or Y. But some results don't show this. For example, enhanced stationary waves, which show intensity in space, or sometimes the ionization rates of atoms. So we're trying to understand better what the predicted output should be, and that's what we're doing in analytics. And what we're trying to do often is look for patterns and look for the theory that we find in the data. Often, so when we come back to data visualization, sometimes researchers have treated patternicity, our ability to look for patterns, as an error and condition. For example, we might have seen pictures of the Virgin Mary appear on a bit of toast or the side of a building. For example, our UFOologists might see a face appearing on Mars. So that gives us type 1 errors, which are false positives, where we see something that wasn't there. But there's also type 2 errors as well, which are false negatives, not believing something is real when it isn't. So we call that a patternicity. And we've got an example here. The artist's name is Giuseppe Arcimboldo. I'm sorry if I said his name wrong, but that's the jurist. And when we look at this, we see a frog basically sitting on the man's face, but we still see it's a man's face. It's a bit of an odd picture. But what it does tell us is our ability to look for patterns and things is almost immediate. So patternicity is an important aspect of us looking for our data. So how can we tame the chaos in our data? We have to understand that change is part of data storytelling, and we have to try and at least understand and predict and control our variables. Feedback is important as well. It's a huge impact in chaos. We have to try and anticipate changes before they occur. Now, data visualization is an important part of that process. And that's why one reason why Power BI exists. It can help us to understand the chaos that we see in our environments and help to visualize it, to help us find those patterns that can help us to predict and control our data. So I've got a few examples where we try and predict the impact before they occur. And one is public debt. So what is it? I've just used this as an example. We have percentages which show our government debt as a percentage of GDP. Those figures will have changed, but that's the idea. There's different ways to calculate public debt, and we can see that. Here's just some examples. We can look at the real GDP growth. We can look at the change in the real exchange rate. So we can look at economic growth, borrowing costs, and any public austerity measures that are in place. So we're going to we'll talk more obviously about COVID's data throughout the day, but I think an interesting consequence of COVID, of the virus, is how can we understand what the impact is on the economy and how can we actually predict that. Another interesting example is how can we know if a country is actually bankrupt? And here's a quote from another Scot, actually, Adam Smith, The Wealth of Nations. When national debts have once been accumulated to a certain degree, there's scarcely a single country having failed and completely paid their debt, and that's probably true. So I'm interested to see what will happen next in the economy. So here's just a quick example of the gross public debt. We can see what the forecasts were, and obviously those forecasts are likely to change quite dramatically as a result of COVID. But we can visualize this data and see straight away that we can understand the forecasts are not looking good. We still got a very high gross public debt for advanced economies. But debts can be really misleading. We can see obviously that at the moment the UK government is certainly talking about borrowing as a result of the COVID environment, and we can see the situation in Spain. It was financially precarious anyway with 4 of the main banks in Spain, but now we see that the tragic situation there with so many people being impacted might actually cause some more real issues there. So we have to think about how debt is structured as well, because itself it can be quite misleading. We'll have a demo at the end and we'll talk more about the practicalities this afternoon. So we're going to talk a little bit about the European Union. Now we've got something called Benford's Law. You may have heard of Benford's Law. It's trying to work out the incidence of the number of times that a digit appears in a sequence. So Benford's Law is used by auditors as part of their fraud detection processes. And what Benford's Law does is it proposes a distribution for the first digits of numbers in naturally occurring data. So they've called it a law, but actually it's more of a guideline, and the data, as we know, can be interpreted in lots of different ways. So I think what's interesting about it is it's just one way we can look at data. There's obviously different lenses that we can put in that. So when we look at things like government accounting and statistics, they're quite similar in nature to financial accounting. So in the EU, for example, there's a pressure to comply with the Stability and Growth Pact criteria. So, for example, governments might make their economic situation look better than it actually is. So there was some suggestion that some countries were manipulating their data in order to join the European Union. There's also been quite some suggestions that some of the COVID's data has been manipulated or underreported, and we certainly are seeing lots of press about that in the UK at the moment, and that's why there's lots of questions about the data because we don't trust it. There's certain things that are surprising in the data. In the UK, for example, there has been a suggestion made this morning that there's been 7,500 deaths in care homes across the UK because of the virus, and that number has not been captured appropriately. And the reason that that suggestion has been made is because deaths in care homes and in the community have not been included in the official figures. The official figures that the UK releases every day are deaths that have occurred in hospital, and there's also discrepancies in the way that that data is reported. So some of the hospital trusts do not report their data at the weekend, but you see their data coming through on a Tuesday. So what that means is we're starting to compare apples and oranges because we're already starting to exclude care home deaths. And the reason for that is it seems like care homes are being treated as if they're hospices where people are being put there on their journey towards death, and it's an unfair way to treat people who are in care homes. It also means that we'll probably never get to the true figure. But what we can do is start to use some analytics and some forensics on the data to try and understand it better, so those people are not forgotten about. So Benford's law has been in the press sometimes, so we're expecting to see the number 1 appear lots of times, right down to number 9 appearing less times. So we can see this is actually, they talk about this in economics sometimes. So Benford's law is also called the first digit law, and it states that in lists of numbers from many real-life sources, the leading digit is in the distribution in a specific non-uniform way. So according to this law, the first digit appears about the digit number 1 appears 30% of the time, and larger digits occur as the leading digit with lower and lower frequency, to the point where having the number 9 appear as a first digit occurs less than 5% of the time. So here we have an example taken from a statistics book. And it's something that you can use quite easily to look at your data when we start to look at Power BI, and we'll have a quick look at this shortly. In 1881, Simon Newcomb picked up a stats book in the library, and what he noticed was that the book was leafed more frequently and for the lower digits than the higher ones. So he started to look at the frequency where number 1 appeared first in a sequence of random numbers. So then Frank Benford articulated this, and what he said was, Benford's law, which he called it, the digit number 1 appears about 30% of the time, and larger digits occur less frequently as the leading digit, to the point where the number 9 appears less than 5% of the time. So then we get to Dr. Mark Negrini. You can look up his articles on the internet. I want to refer you to him. He published a thesis that noted that Benford's law could be used to detect fraud. So say, for example, someone is fiddling their expenses. They're more likely to put down numbers that start with 7, 8 and 9 rather than 1, 2 and 3. And the reason they do that is they're trying to make the numbers look as if they're quite normal numbers, but the numbers that they start to choose intuitively, they start to pick higher values. So you can use it to detect people like expense fraud, and it's been applied to some of the COVID data as well. So I'll refer you to some of the theory around that too. So invented numbers are less likely to follow Benford's law, and that's the discrepancy between that distribution and the actual numbers that you see can be an indication that something is wrong with the underlying numbers. So you can use it for all sorts of things. You can throw your own personal expenses at it and look for this pattern as well. But it has to be data that actually means something. Benford's law doesn't hold in certain doesn't hold in lots of different cases. It doesn't apply to heights. 152 centimetres happens to be my height. Lots of people are going to start with a 1 in that case, so it doesn't tell you anything. Nominal data like telephone numbers obviously don't work either. And we use it for auditing, and we can use it in Power BI. So we can check the data. Benford's law, we're looking for outliers. You can see it in the acquisition of data. Missing data is obviously important as well. So we can look for, when we're auditing data, we can look for strange behaviour in the processing. Obviously, there's process issues as well. We can look for due diligence not being followed or just not being implemented due to a lack of safeguards. So there's different ways that we can use data visualization in Power BI and in R, for example, in order to have a quick look at Benford's law. And we can also look at outliers, and we can look at missing data as well. So here's just an example of where we see this happening in some of the European GDP data. So the number 1 appears almost 30% of the time as the first digit in the sequence, and that is actually close to what Benford's law actually states. So when we look at the deficit surplus numbers, we can see that they actually follow Benford's law quite similarly. So when we look at the European data and we visualize it, this is obviously just in Excel, we can see that actually we start to follow this pattern when we look at the deficit surplus data using Benford's law. So we can visualize it in different ways. Obviously, that's the line charts. Okay, so a quick summary before we have a quick look at it in Power BI. So Benford's law is not the final word, but it is a start for where we could go with Power BI and visualizing and understanding if there is any fraudulent aspects to the data. We have to prove everything and keep asking ourselves the questions. We need to also think about repeatable principles in science. Occam's razor just simply states that sometimes the simplest answer is the right one. So what we can do is just think about, sometimes people confuse likely outcomes with possible outcomes. So sometimes when I'm dealing with customers and we're architecting a system, they'll find an edge case and they'll say, oh, we can't build this system or do it this way because of this edge case. And what they're doing is confusing likelihood with probability. Now, it's possible I'm sat here in a Santa suit addressing you all, but it's not very likely. And just because something's possible doesn't mean that it's likely. So I think it's quite interesting that to apply Occam's razor and just think about the likelihood and the probability. They are almost two interesting ways to look at data. So repeatable results by someone else. Now, when we start to look at artificial intelligence, everyone keeps saying AI's had all of its winters and artificial intelligence is not going to go away now, and that the AI winter are things of the past. Actually, I'm not sure that's totally true. I think what I see is organisations starting to look at Power BI and look at artificial intelligence, and because they're not always successful with it, they start to drop it a little bit. So it might not be an artificial intelligence winter, to quote Shakespeare, but what it might be is a slight frost instead. So we also need to think about the context as well, because data is fairly meaningless without it, and we need to consider what the context actually means. So when we talk about context, why is the data being reported the way that it is? So I talked about the data in the UK, where care home deaths are recorded on a Wednesday, and they may not be capturing them all. But the rest of the data, most of it has been captured on a daily basis, but not always. We don't see weekends data come through for some trusts until a Tuesday. So it starts to look like we have got a spike on a Tuesday and that things are cooling down a bit over the weekend. So sometimes over the weekend and on a Monday, we start to hear that the numbers are slowing and things are looking better. but actually just simply that not all of the data is being reported. I need to check this out, but I think there's also a difference between the times in which Scotland reports its data in terms of how that compares to England and Wales. So when we talk about UK data, I think the timing cut-offs are slightly different. We know that Nicola Sturgeon reports her figures and has her State of the Nation address daily about 1 o'clock, but the English government do it about 5 o'clock, or the UK government rather, I should say. So there's a lot going on with the data, even when we start to look at confirmed deaths. So what I want to do is take you through some data sources. We'll have a quick look at Benford and Power BI as well. I'm just going to check Teams to see if there's any questions. I can see lots of chat. I don't know if that's a good thing. All right, I see the GIF. I hope that's okay. Data is super interesting. There's more to it. Okay, no questions yet. Okay, that's great. Okay, good. All right, so what I want to do is I want to show you where we can get some good COVID data. Someone asked me yesterday, how can we get COVID data? So I'm going to quickly set up a browser. So for those of you wondering, oh, I'll close my portal. There we go. I've been looking at text analytics. We're not talking about that today, but it's something I've been looking at. So you can ignore that. So actually, when you move on to Wikipedia, there's actually COVID data appearing here. So COVID data, and it's what we were looking at was confirmed cases. Okay. So there's actually, when you go into Wikipedia, I know there's lots of other sources as well, but if you're just looking for a quick grab of some data, Wikipedia have started to release some of their CSV files, and you can download them as well. So I did find some for China. And the reason that they're showing you this data is you can start to see it appearing on the left-hand side here. So I believe, actually I'll go back and look for CSV file. Okay, so let's see if we can find it here. So you can dig it out. You can use that as well. There's tables there, but I did actually find a CSV file. I will dig it out for this afternoon rather than spend a lot of time looking for it. I'm a bit frustrated with myself not being able to find it because it jumped out at me yesterday and I had it then. So I'm just checking it on another system. I know that I've got it. So while I dig that out, let's have a quick look at Power BI. So I'm just going to use a Power BI desktop. So there's data underlying some of these images, and I wanted to dig out some of the data, confirmed deaths, where there's a map, and there is an interactive timeline as well, and we can see the larger version. So yes, because some of the data was coming from down here. I'll dig it out later, but you can see where the template documentation is coming from. Okay, so I'm just going to look at the Power BI desktop. Okay, so for those of you that are not familiar with R in Power BI, I'm just going to show you quite quickly how we can put those together. For those of you who do know it really well, please bear with me. There's a range of different people with different skill sets on the call, and what I'd like to do is just try and make sure everyone's in a good place. So what I'd like to do first of all is show you how we can use Benford's law just simply to generate some data, and then we'll visualize it. And we're going to do that using R. So what we see here, and I should have started to zoom it up, sorry, but I hope you can see this chart. What we see is the first digit appearing 1, 2, 3, 4, 5, so on and so forth up to 9. And what Benford's law is doing is I'm generating some random numbers here between 1 and 9, and then we are using a bar chart here, and then I'm going to plot that. The data set is called digits. So in this particular example, what I'm doing is I am just generating a random set of digits. And basically what I'm doing is then working out using Benford's law, how we can work out how many times the number 1 appears as the very first digit, how many times it appears as number 2 appears as the first digit, how many times number 3 appears as the first digit, that kind of thing. So when we visualize just that digits data, we can see that the number 1 appears most frequently. According to Benford's law, we'd expect the number 1 to appear 30% of the time, expect the number 2 to appear 18% of the time. So when we throw some transaction data at this, what we do see is we're kind of expecting the data to follow this pattern. It doesn't always. We talked about telephone numbers, and there are lots of different examples where it doesn't. So for example, if you don't have much data, then it doesn't tend to show this pattern. But it's something that you might start to use when you're analysing data. You can use it for genome data as well, if there's looking for fraudulent data in that. So, but this is a pattern we expect to see. So what I've done is I've used R here, just a very small example, where we've got some code and I'm assigning that function, creating a function called benlaw, which is calculating the Benford's law here, and then I'm using that function with this data set, and then I'm just visualizing it. So we can add in our codes to Power BI. The way that we do that is I'm just going to copy and paste that. I'll start up a new chart. So we can see on the right hand side here that we've got some visuals. We've got R and we've got Python. I'm just going to use R for the moment. So when we click on R, we get this visual appearing at the very top. And it appears here. So I can click on that. And you can start off, first of all, we can, even though I'm not using this data for this particular chart, this allows me to set up a communication between R and Power BI. What it does is it will set up what's known in R as a data set. If you're familiar with reporting services, we have the same terminology there. And what a data set is going to do is just simply a table of data with rows and columns, and the mix and the data types in each of those columns tends to be quite mixed. So there might be an integer, there might be a column of strings, there might be one of dates, that kind of thing. So the reason R can do this is because we have got something in R called a data frame. And there are different ways of storing data in R, but this is one of the most popular ones because it's fairly powerful. And what we do is in Power BI, I'll mark it yellow, we click in our columns. And the columns that we click on in the right-hand side of Power BI appear as fields just here. So I've added in date, and that's what we see. So all of these columns are perceived by R as a data frame, and they're assigned to a variable which we will just call dataset. So in this example here, I'm not going to use any of this data. I just want to show what the Benford's law looks like. So when I hit the play button over here in the right hand side, that should then bring up a little chart here. We can add in more code to make the chart more interesting, but we can do that later when we start to look at Power BI for real. So we talked a little bit about visualizing the data, tying R and Power BI together. What I did was I took the data from Wikipedia, and I promised I would dig out the source. I'll do that this afternoon. So this is the line chart, and what we're looking at is the number of confirmed COVID cases by year, by country, by day. So we see the timeline appear in the x-axis, and then we start to see the number of confirmed cases over time. We see China starting to level off. We see Belgium appearing here. Now I'm interested because these are number of confirmed cases. So I know that the number of deaths chart looks quite different. So, but we do see that leveling off, and we see Wuhan, for example, starting to open up again. So that's great. So we can start to, what we'll do later on this afternoon in the session at 1 o'clock UK time is start to use some of the Benford's law against some of this COVID's data, just so we can see the patterns that are available in it. But I thought it'd be interesting for you to see. We can take this data. In the source in Wikipedia, it does need some massaging. So in the underlying data, we've got the country information here, and we've got the country ID numbers. So we can start to use the ISO 3 configuration to start to read the data. So if it can't find that particular ID, the ISO 3 code for the country, then it just puts in X. So we can see the figures for the West Bank and Gaza there. Then we start to see Angola appearing. So of course, obviously, we can start to map the data as well. Remember, this is confirmed cases. So we see here US having a high number of confirmed cases. And then we see the number for China appearing over here. So we can start to look at this data this afternoon. Before I proceed, I'm just going to check to see if there's any questions in Teams. Make sure you're all okay. All right, what version of Power BI have I installed? I'll just show you. Yes, I'll have a look in Power BI. About. So hopefully that helps. That's the version I'm using. Okay, so what I wanted to do was just simply try and take you through some of the data. So I can hear beeps going off in Teams. I just want to make sure everyone's okay. That's all right. Thank you, Christian. Thank you for joining this morning. I can see there's quite a few people. So I'm just checking the time. We were supposed to have 45 minutes. I'll have and then questions. I'll just have a quick recap before I take any questions. So I'm just looking up some other reference I wanted to show you. So what I will do is I'll take you a quick tour. Brave is here. I want to show you, I know it's not Power BI, but I wanted to give you some examples of Benford's law. So we can see that it happens in real life. Okay. So there's plenty of references here. You can use Excel to calculate Benford's law, detecting numbers of regularities. I thought it was building size as well, the length of buildings. So here's an interesting example from datagenetics.com. I'll just show you this one. So if you plot the account of the first digit, you get this chart, and this is what we saw in Power BI. So we can see that when we throw some other data at it, we start to see this pattern appearing. So when we look for it, we see in different places. So distribution of the digits of altitude of the top 120 towns in the world. I know it's a terrible chart. We could really tear that one apart, couldn't we? But you can see that it starts to appear in this pattern as well. So there's some applications of it, and the ones that we used were actually looking at Benford's, looking at some fraud. Okay, so with that in mind, just a quick summary, and then we'll start to take questions. Oh, sorry. Go back to where I was. Yes, I did a few other things just to sort of share as well. Okay, so why have we got to where we are with looking at our data in this way? And the idea is that what we're trying to do is boil everything down to the simple. We're constantly creating new models of the world. So we think about Newton, we think about Einstein, building on Newton's work. But life isn't that simple, and networks are complex, changing and adapting. And what we're seeing in the language of the digital era is that networks are becoming more powerful, where we focus on the connections, the nature of the relationships and the intensity of the information. That's why the COVID data is so interesting, because we see these discrepancies appearing across the world. We're trying to deal with global data, and we are trying to make data as simple as possible. So I love this quote by Nicholas Carr, by the Shallows. We live in a culture of now, and consumers of data act like active elements in a network. They're not necessarily very passive. But when we talk about networks in a culture of data, we need to talk about speed. We need to talk about people getting their data fast and how they consume that and what it looks like in an organisation. We have to adapt to the inside of our companies to markets that are changing faster ever than before. So there's a big shift in the way that the world works, and it's harder to measure. So we think about the innovation network, we think and work about the social network as well, and the structured network. Because when we get to some organisations, there is a tipping point or an inflection point where they just can't handle the amount of data that they've got anymore. And the world's digital is no longer a meaningful word in some ways. Analog is the exception rather than the norm. But trying to keep up with a world of data reveals the slowness of some organisations to catch up. And that's why I think Power BI is important. We're trying to work out how we can get data to people really fast and trying to give them the patterns that they need in the data as quickly as possible. So we're in a constant fast food diet of data. We're moving from solid meals to fast food, and we're snacking constantly in the data that we have. But it's not always good for us to do that. We need to think more carefully and more critically about the data sources, which is why Benford's law is pretty interesting, I think. Are we snacking on the right things? Are we having fast food or a quick snack of vegetables? So if we look at the laws of physics, for example, Newton's laws worked really well until objects moved really fast. And that's when Newton's law starts to break down. So Einstein's insight was always thought that the speed of light is an absolute constant because his physics worked better when things move really, really fast. But perhaps his real insight was that when we change our perception beyond the familiar world that we know, our principles of operations actually change, and we have to rethink what is normal. The normal mechanisms don't work anymore, and sometimes we need a new conceptual architecture to think about our data and how organisations function across boundaries when our external clock exceeds and outruns our internal clocks. So we live in a culture of shock of dealing with a lot of data. And it's important to think about the structure of those data and to question it often and always. We need to look at the bigger picture sometimes, at the patterns in the data. Here, I love this slide, entropy, organise all you want, it won't matter. And we need to think about the language that we use and statistics, and not always just cause and effect. It's about trying to work out where the structure lies if it does exist. I love this example. This is the proposal for the internet done by Tim Berners-Lee. And this is Tim Berners-Lee's paper from 1989, where he proposed a loosely interconnected web of computers across the internet. And he did that when he was doing some work at CERN. And the thing that I love about this is one of the reviewers said that his paper was vague, but quite exciting. And we are where we are with that. But I think it's about people's interpretation, what they bring to it when they look at the data. Because our society is becoming more and more based in networks, and we can't think very linearly anymore. We need to think about the patterns as well. And it's almost like trying to develop a new language when we think of data, when we're trying to understand data at speed. It's a rate that outruns our internal clocks. And we need to see information as a flow. Where's it coming from, a source, and where's it going? What are we going to do with it? What does the analytics look like? How clean is the data? The sort of things that people don't want to think about always. And information flows faster through a network, which is why we're seeing more and more of it all the time. So how do we change? We have to think about connecting to our customers better internally and externally. We have to think about the social network and how we influence that. And I think that's what we see with the COVID data. And we are questioning it, and we need to keep questioning what is happening. The news this morning about the care homes did not surprise me. The number didn't surprise me either, because some of the other figures are showing that between 25 and 50% of all deaths are occurring in care homes, and those. So I think the data is much higher. The numbers are much higher than we are being led to believe, but we need to keep questioning it. So sometimes to do that is to organise small teams, and we see social citizens and data questioning and analysing this data. And we need to think about our real-time data as well. So we talk about the Internet of Things, like Hinson. I believe maybe that's the wrong phrase. Maybe we should think about the network of things, because data on its own is not always very interesting. It can be about the context as well, and how we can make patterns, and how we can organise ourselves in very complex adaptive systems that we're generating for ourselves. And maybe it's less about the structure, but more about the patterns, and just simply trying to keep up. Because we have lots of information and lots of data, and that's what Power BI is trying to solve. We're trying to use it today to understand COVID better. And we're looking for the dot joiners as well, and a network of networkers, to see how people can actually take this data, understand it, and really use it to understand not just the data points, but the relationships, and put all the pieces together. So to come back to the original point, we are trying to figure out, get the point of chaos, where our adaptive systems grow at the edge of chaos. We go from disorder to order, and then back to disorder again. And we need to be creative with our data as well, and discover any patterns in there with fresh eyes, like Einstein did. So with that, I see it's 10 to 8 in the morning my time. I'm just going to go back to Teams and see if there's any questions. But it sounds like it's probably time to wrap up. And I believe in 10 minutes we have Mark Wilcock appearing at that time. So it's well worth hanging around to listen to Mark. He's a great speaker, and I think you really enjoy his session. So with that, does anyone have any questions? I'm just checking Teams. If anyone wants... Oh, thank you. I can keep talking about anything, but this is a good idea. Thank you. All right. So I don't know how you want to deal with the handover to the next speaker. I'm assuming Mark will introduce himself. I'm happy to try and introduce you, Mark, but it's probably better that you do that.
Thanks, Jen. I can introduce myself.